All right, let's go ahead and get started. I want to welcome you back to Unit 4. This is the periodic table. So we've looked now at many different aspects of the periodic table, and I want to look again at the rows of the periodic table and what those rows signify. We have 7 rows on the periodic table, and these rows correspond to the highest main energy level that an electron in any atom resides. For example, let's take magnesium. Find magnesium on the periodic table. It's number 12. Now, notice it's in the 3rd row. What does this mean in terms of the highest main energy level that an electron occupies in a magnesium atom? Well, let's write the electron configuration for magnesium. Off the periodic table, read remember the S, the P, the D, and the F blocks. Remember the first main energy level is the 1st row, second main energy level, 2nd row, and so forth. So let's write the electron configuration by going from left to right, top to bottom, starting with hydrogen. So we have first main energy level, S block. We'll go to helium now, 2. So 1s2. Let's go to the second main energy level. Now we're at lithium, S block, and we'll go to beryllium with a 2 right there. Now let's continue in the second main energy level, 2. P block, however, and let's go to neon with 6 right there. And then finally, third main energy level, S block, 2 electrons in that S sublevel. So what do we now know? We now know that the main energy level corresponds to the row on the periodic table. That 3 means that the last electron is in the 3rd main energy level, and that 3rd main energy level corresponds to the 3rd row on the periodic table. Now I want to get back to ionization energy. Remember that the first ionization energy is the energy required to remove a single electron. All right? So ionization energies increase as you move up and to the right on the periodic table, just as do electronegativities. Ionization energies get higher and higher and higher as you move up and to the right. Now, the second ionization energy is the energy required to remove a second electron. It's always larger than the first ionization energy because it's just harder to remove a second electron than a first electron. So always expect the second ionization energy to be greater than the first ionization energy. But a jump in ionization energy occurs when inner shell electrons are removed. Let's take an example. Let's take beryllium, for example. So beryllium has the electron configuration 1s2, 2s2. Okay? Now let's imagine what would happen if I tried to remove the first electron. So if I try to remove the electron that's in, or one of the 2 electrons that is in the second main energy level, S sublevel, then that's going to be fairly easy, relatively easy, right? So that would make it 1s2, 2s1 after I remove that 1 electron. But if I remove the second electron, that takes both of these electrons away, leaving me only with 1s2. My point here is that removing the second electron is harder than removing the first electron from the second main energy level, but removing another electron, a 3rd electron from the first main energy level, is going to be much harder because you're removing electrons or attempting to remove electrons from inner main energy levels, and that's going to be very difficult. One last point, and that is this: reactivity increases as you move down a family or group. If you move down a family or group, you can expect reactivity to increase. So let's compare 2 alkali metals. Let's take lithium and potassium. Which would be more reactive, lithium or potassium? Well, potassium is lower in that family or group, so potassium would be the most reactive. Now let's compare nitrogen and arsenic. Nitrogen is number 7, arsenic number 33. How do they compare? Well, arsenic's lower on that family, and lower in that group, so arsenic would be more reactive than nitrogen. Now let's try this one, neon or krypton. Now this is kind of a trick question because notice that these are both noble gases. The fact is that neither one of these is reactive. They're noble gases. They don't want to react with other elements. So the answer would be between neon and krypton, neither one is more reactive. All right, let's go back now to ionization energy trends for just a moment. As you move from left to right on a periodic table, ionization energies increase. We know that. Now this is because the atoms are getting smaller and the nuclear charge is increasing. So it's harder to remove an electron as you move from left to right because the ionization energy, because the nuclear charge is increasing. All right? Thus, it's harder to pluck off the first electron, right? It's harder to pluck off the first electron as you move from left to right. Now, as you move down a family or a group, electronegativity decreases since the next atom down has its last electron in a completely different main energy level, one that's much further away than the previous main energy level. So notice in the graph below what happens as you move down the noble gases family or groups. So let's take a look at this graph charting atomic number versus ionization energy. As we go from hydrogen to helium to lithium to beryllium and so forth, in a particular period, let's go from 3 to 10, that's that's lithium to neon, the ionization energy is increasing. But notice what happens when we go from neon to sodium. What's going to happen is the ionization energy is going to drop dramatically. And so we see this pattern. Higher and higher and higher as we go down a family, as we go across a row, higher and higher and higher ionization energy as you move across a period, but then it drops as you go back down to the next period, then rises again and so forth. But let's look at the trend just in terms of the noble gases. Helium versus neon versus argon. As you move down that family or group, the ionization energy is going to decrease. All right, the ionization energy decreases as you move down a family or a group. All right, now let's talk about the second ionization energy. In fact, let's look at a specific element. Let's say sodium. It's relatively easy to remove the first electron to make sodium ions. That's Na+. But the second ionization energy is going to be extremely high. Now, why is that? The reason is that sodium ion is now isoelectronic with neon. Once you remove that first electron, the electron configuration is going to be like the previous noble gas, which is neon. It's not going to give up that second electron without a big fight. It is happy, right? Having that first electron removed was easy, but having the second one is going to require a lot more energy. Thus, the very high second ionization energy. All right? Folks, we've got some questions to answer here, but I think we'll do this one on the next screencast. So I'll see you on the next one. Thanks. Bye-bye.